This is Physics 2212, Lab 4, Circuits. The purpose of this lab is to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential difference in the circuits, and examine the behavior of ohmic resistors and capacitors. Fundamentals are conservation of energy and charge, Kirchhoff's loop rule, node rule, series and parallel circuits, Ohm's law, steady-state circuits, capacitance, and time dependence, and resistor-capacitor circuits. Part 1, the circuit had two 1.5 volt batteries, 2 ammeters, and 2 resistors with 4,700 ohms respectively. Predictions is that total resistance is 147 ohms, and the I1 current, I2 current would equal 0.02 amps. The actual reading was 0.02 amps, and if one of the ammeters was connected in reverse, the reading is opposite, so it's negative 0.02 amps. And the reading when replacing one ammeter with a voltmeter, the voltage was 3 volts, and I current was 0 amps. Current is 0 because of the open circuit. Voltage is 3 volts because potential difference across the gap equals that of the power source. Part 1 continued. The potential differences in the loop shown here should follow their loop rule, so that the potential difference for a round trip equals 0 volts. Got potential difference across AB, the battery is just 3 volts. BC is 0 volts, CD negative 0.96, DE 0, EF negative 2.04, the rest are 0. You sum those all together, you get 0, follows the loop rule, and the current is 0.02 amps. Adding a voltmeter does not change the ammeter's reading because the voltmeter has a very high resistance, so no current flows to the voltmeter, just leaves the original loop as it was. So this is a graph for the potential difference as it goes along the circuit, and this is an increase in voltage as it goes through the batteries, drops a little bit as it goes across the resistor, drops a lot more as it goes across the second resistor because it's a higher resistance, and then across the ammeter because it's 0 resistance. Next part of the experiment, I had to add a 100 ohm resistor in parallel with another ammeter, and this created a parallel circuit right here, so that would decrease the equilibrium resistance because of an extra path, and this increased the total current because of the low resistance with the same power source, the potential, and calculations to see if my predictions were matched like the experiment. Our 47 resistor was 48 ohms, 100 was actually 102, the wire is 0 and 0. So the calculated resistances are higher than predicted due to the low precision of the ammeters. The next part was RC circuits, and the first one shown here is a 9 volt battery, a 10 ohm bulb, and 200 millifarad capacitor. At initial connection, the bulb is really bright, and then it quickly dims over time. Current decreases from max to 0 pretty quickly. Same thing happens when the battery is removed and the bulb is connected to a charged capacitor only. The bulb is bright and then very quickly dims as the capacitor loses charge. The current decreases from max to 0. And capacitor, a 10 ohm bulb, took 10.3 seconds to charge and 12.1 seconds to discharge. Capacitor, the 20 ohm bulb, took 17.2 seconds to charge and 22.2 seconds to discharge. The next part of the experiment showed the time-dependent voltage across the discharged capacitor. We have this equation, and then taking natural log of both sides, we can get an equation by using these values, plotting natural log of delta V or VO gives us this line that's linear. So the slope of this graph is negative 0.1671. The reason this is important because the experimental RC, which is time constant, is equal to negative 1 over the slope, which is shown here as 5.98. This is using the 9 volt battery, 30 ohm bulb, and 200 millifarad capacitor. So the predicted RC is equal to the resistance times capacitance, which is 30 times 0.2, which equals 6 seconds. And the computed RC value is agreed with the RC value of the circuit simulator, as shown above. So some model discrepancies. There are most likely no model discrepancies because I used a computer simulation of the ideal circuits to conduct the experiment. However, the simulation was not always precise enough. Source of error. The only source of error in the experiment was human error, and according to the amount of time the capacitor took to charge and discharge 100% accurately, everything else should be valid because the experiment used an ideal simulation. What if you're doing this in lab in real life and use an actual ammeter instead of an ideal simulated one? So the real ammeter would have actually like a resistance greater than 0. So this would increase the overall resistance of the circuit, decrease in the current, so decrease the current in the circuit. And if you're doing this lab in real life and use a real battery to charge a real capacitor and a resistor in the circuit, how quickly would our ideal model predict the capacitor reach full charge? So in real life, real life, the wires have some resistance, so it would slow down the charging. If you use an ideal simulation, no resistor in the circuit, then the wires have no resistance, so it would charge basically instantly. But in real life, there's resistance, so it doesn't. Conclusion: to calculate accurate values for a circuit, the circuit must be as close to ideal as possible. The wires and ammeters must hit the lowest resistance possible. In circuits with capacitors and resistors, current and voltage are time-dependent and decrease non-linearly over time. The node and loop rule are very helpful when observing and calculating properties of a circuit.